Geographic Information System, Surface Models Part 2. In this chapter, we will discuss about the digital surface model, sources of digital surface model, application of digital surface model, digital terrain model, difference between digital surface model and digital terrain model, quality of the DSM and DTM, representation of digital terrain model, sources of digital terrain model, application of digital terrain model. Three-dimensional digital terrain or surface model, known also under the abbreviation DTM, DSM, are the result of space mapping of an area. Digital surface models are used especially for 3D modeling of towns and landscapes as a basis for demonstrative visualization and various GIS applications. A survey is usually performed using aerial survey photography or laser scanning. It is possible to use classic geodetic methods or GNSS as well. Digital terrain or surface models can vary in number of captured details, differences in the way of landscape rendering. It is necessary to draw the line between the digital terrain model and the digital surface model. The digital surface model is a digital surface, or the other hand is a term used confused with the DEM. In a DSM, surface typically refers to the topmost, that is the radar reflective surface for a given area. This includes all exposed objects or surfaces in the scene registering the height of a bare earth or the ground surface only when nothing else is above it. So far as DSM, while a laser or a radio wave will interact with the first object it encounters, whether it is a treetop or a building or an exposed ground. A DEM retains only ground points in order to develop a ground height model. Digital elevation model is one of the most important spatial data set in many geographical information systems. It is defined as an ordered or unordered digital set of ground elevation, that is the spot height for terrain representation. In literature, there are three commonly used terms related to this, namely digital elevation model, that is DEM, digital terrain model, that is DTM, and the digital surface model, that is DSM. The distinction among the three terms is not clear and universally agreed, but some common tenets may apply, as a DEM is a bare land surface model which is supposedly free of trees, building or other non-ground object. A DSM is an elevation model that includes the tops of everything, including buildings, treetops and ground where there is nothing else on top of it. A DTM is a more generic term referring to a DEM with one or more types of terrain information, such as the terrain morphological feature, that is the drainage pattern, the soil properties, etc. When dealing with only one terrain information type, that is height, this is a DEM. Obviously, DEMS is a subset of digital terrain models, that is given by Lee and Zhu. Task of digital terrain model. A few major tasks can be identified in the study field of DTM, namely the terrain data capture, DEM generation, DEM manipulation, DEM interpretation, DEM visualization and DEM application. The objective of the data capture, DEM generalization and manipulation is to achieve digital representation of terrain. The ultimate outcome from these tasks is an error-free and hydrologically sound DEM at the right scale. A digital surface model is an elevation model that captures both the environmental's natural and artificial feature. It includes the top of the building, trees, power line or any other object. This is seen as a canopy model and only sees ground where there is nothing else above it. The digital surface model represents a true copy of an area. Its georelief contains all natural and artificial elements that are related to the concerned area. For example, trees, vegetation, buildings and other objects. Digital surface models are primarily used in 3D modeling of towns and landscape or for visibility analysis in GIS. Various visualization measures can be generated from this model. In a LiDAR system, pulses of the light travels to the ground. When the pulse of the light bounces off its target and returns to the sensor, it gives a range, a variable distance to the earth. Hence, how the system earned its name of light detection and ranging. In the end, LiDAR delivers a massive point cloud with elevation values, but height can come from the top of a building, trees, canopy, power lines and other feature. A DSM captures the natural and built feature on the Earth's surface. A DSM is useful in 3D modeling for telecommunication, urban planning and aviation. Because objects extrude from the Earth, this is particularly useful in these examples. The digital surface model. The digital surface model extruding features are tree canopy, runaway approach zone encroachment. In aviation, DSMs can determine runaway obstruction in the approach zone. Vegetation management. Along a transmission line, DSMs can see where and how much vegetation is encroaching. View obstruction. Urban planners use DSM to check how a proposed building would affect the view shield of residents and businesses. The main data source for creating digital surface models, digitized maps and 3D modeling are topographic maps. Provides a geographic reference that stores coordinates and elevation information about terrain features such as terrain, building, structures, roads, rivers, land use, contours, administrative boundaries and so on. Remote sensing materials obtained in stereo mode are used to create digital surface models and orthophotos. A cloud of point obtained by laser scanning. Because DSM represent the bare earth and all of its above ground features, they are particularly important in urban planning. 3D surface model can increase the understanding and explanation of complex urban scenarios, especially a built-up area change with time due to urban expansion. DSMs are ideal for runway approach zone encroachment in aviation and urban planning to check how a proposed building may affect views. The digital surface model is used in a variety of planning, analysis, visualization and modeling applications, including localities for various purposes like architectural planning, tourism, virtual tools, etc. Navigation system, intelligent transport system, forecasting of urban risk, telecommunication, that is positioning of mobile phone transmitters, in the mapping of flood risk, vegetation management, decision making, disaster management. The digital terrain models or DTMs have different definitions depending on where you are in the world. Digital terrain model is a topographic model of a bare earth, that is the terrain relief. The data files contain the spatial elevation data of the terrain in the digital format, which usually presented as the rectangular grid. Vegetation, buildings and other man-made, that is artificial feature are removed digitally, leaving just the underlying terrain. DTM is considered as a synonym of bare earth DEM. DTMs are often confused with DEMs. The main difference between the two models lies in the fact that the DEM generally takes into account all persistent objects on the ground, that is vegetation, buildings and other artifacts, while the DTM shows the development of the geodesic surface. Bare earth refers to the fact that vegetation and human-made surfaces such as trees and power lines are filtered out with DEMs. Regardless of the definition, a DTM is essentially a three-dimensional digital representation of a surface consisting of x, y and z coordinates. Within a DTM, you will find height and elevation as well as natural features such as rivers and ridge lines. However, these subtle differences between DEM and DTM are most evident in urban areas where the prevailing high-rise buildings. DTMs can be created through various methods including digitized contours and even from the DSMs using the difference between the height value of the trees and the buildings and their local neighborhood. Therefore, DTMs can also be created from any of the methods used to generate DSMs from LiDAR to stereophotogrammetry as well as SAR, DGPS and ground surveying, all at the varying levels of detail. A DSM captures both natural and human-made features of the environment, whereas a DSM shown a DTM only retains features of a bare earth terrain such as rivers and ridges. A DTM can be derived from a DSM, but the same is not true vice versa. DSMs include objects on the earth's surface, whereas DTMs do not. For most LiDAR applications, the focus is placed on the DEM and DSM as above as defined, with DTMs more applicable for GIS and cartographic representation. Several factors influence the quality of DEM derived products, that is, the vertical resolution, terrain roughness, sampling density and resulting spatial resolution or pixel size, terrain analysis algorithm, interpolation algorithm, reference 3D products with quality mask containing information on the coastline, snow, clouds, water bodies, etc. Common mathematical representation for DTMs include regularly spaced grid, that is the 2D raster or matrix form, irregular distributed 2D points, that is variable point distances, and 1D profiles, contours, that is lines of contrast heights. Triangulation of irregularly distributed 2D points known as triangulated irregular network (TIN) allows incorporation of terrain break lines, that is ridges or valleys, to better represent the terrain, but are more complex to handle than gridded DTMs. The gridded DTMs are derived from TINs through computation of height values at 2D raster location using some interpolation techniques. Example, fitting of linear or curved surfaces, least square production, kriging. With increasing spatial resolution, gridded DTMs tend to approximate break lines and extreme location better, while containing more redundant information in flat terrain. DTMs are most commonly provided in the terms of regularly spaced grid, which allows simple data handling, manipulation and storage. Another efficient but less common way to present a DTM is through a set of surface spherical harmonic coefficients computed from a high resolution 2D raster. DTM heights at arbitrary location are then obtained through series expansion of the coefficient. Currently, those spherical harmonic DTM representations reach spatial resolution of about 2 km, equivalent to harmonic degree of 10,800. From a range of sources relying on the ground-based, airborne and spaceborne surveying techniques, DTM data is available for parts and the whole of the Earth's surface at different spatial resolution. Traditional ground-based methods, example Kenny and Petrie in 1990, are very accurate but tedious and therefore most limited to small areas. Field surveying based on tachymetry delivers terrain height at selected locations. Satellite surveying techniques, that is GNSS, provides terrain heights at discrete location or along profiles, for example along the road. GNSS heights are sometimes used as a check on DEMs from remote sensing. Another source of terrain height are digitized contour lines from existing topographic maps. Modern airborne and spaceborne sensors are considerably more efficient for terrain surface mapping than ground methods. This is because the terrain is sampled at vast number of locations in real time, and the sensor movement in air or space allows mapping of regional or even global profiles. Important mapping sensors on flying platform are imaged based, which is present in the photogrammetry, the laser based present in LiDAR, and radar based, for example, radar interferometry. Photogrammetric methods use overlapping pairs of images showing the terrain from different angles, that is the stereo principle. The stereoscopic processing yields terrain heights for ground points captured and identified in both images. Aerial photogrammetry is used for terrain mapping at national scale, and satellite-borne images, for example, SPOT, ASTAR or ALO satellites globally are being used. Dense vegetation cover and clouds reduce the completeness of the DTM data from photogrammetry. To establish terrain heights with laser-based method, travel time of short light pulses emitted from a laser measurement system and reflected by the ground is measured. The rotating mirror spread series of laser pulses into the swaths, allowing sampling terrain height profiles with high spatial resolution. Over vegetated area, there are usually multiple return pulses. For example, reflection of the top of the canopy and at the ground, which provides information on the bare ground elevation and the vegetation height. Airborne LiDAR is a standard in generating highly accurate and detailed regional DTMs and DSMs in efficient manner. Spaceborne LiDAR deployed, for example, the ISAS satellite, are well suited to obtain DTMs over the Earth's ice sheet. Similar technique used aboard planetary missions provided highest resolution DTMs for Mars and Moon. Different to LiDAR, radar-based techniques operate with microwave signals, which are cloud penetrating. Signal travel time phase or of phase differences are used as a measure. Commonly used radar variants are SAR, synthetic aperture radar, with increased imaging resolution through the use of artificial apertures, and INSARs, interferometric SAR, where the stereo principle is applied with two nearby antennae recording the same radar pulse. The differences in signal phases depend on the terrain height, so can be used to derive the DTM data. In steep terrain, radar-based topography mapping may produce voids in the DTM caused by the so-called radar shadows or signal layover. The most prominent examples for spaceborne INSAR is the Shuttle Radar Topography mission. Radar systems are being operated abroad planes for spatial applications too. For example, to obtain elevation data of the rock beneath Earth's ice sheet. In a planetary context, radar was used to obtain a DTM of Venus, a permanently cloud-covered planet. Terrain model plays a fundamental role in geosciences and engineering and have numerous applications. They can be used to calculate derived quantities such as volume, slope, curvature, sun exposure, hill shade and gravitational attraction. Application example for DTM includes its uses as a base layer in geographic information system. For example, for planning of engineering structures like roads, railways, canals. In hydrology, for example, in drainage and catchment area analysis. Used in coastal protection, that is in inundation land. Mass movements in the mountain areas, rendering visualization and topographic maps. Planning of radio network and alternative energies like power plants and rectification of photogrammetric images, that is orthophotos. In the narrower field of gravity field, modeling and physical geodesy, DTM data is a pivotal data source for providing geometric information of the topographic masses. Using gravity forwarded modeling techniques, the gravitational attraction of the masses is computed from DTM data and can be subtracted from the observed gravity values to highlight signatures of mass anomalies in the Earth's interior. It can be also used as reduction in geoid determination or utilized to predict a detailed gravity field over otherwise less surveyed areas. For these examples, the availability of DTM rather than DSM data is important. The concept of DTM is not only limited to Earth's visible terrain surface, it also finds application in bathymetry, that is, digital bathymetry models describing the geometry of a sea floor, polar geodesy, digital bedrock models to describe the rock below the ice sheets, and the planetary signs, that is, the digital elevation model of the planetary surfaces, among many other areas of application. There is no universal usage of the terms digital elevation model, digital terrain model and digital surface model in scientific literature. In most cases, the term digital surface model represents the Earth's surface and includes all objects on it. In contrast to DSM, the digital terrain model represents the bare ground surface without any objects like plants and buildings. While DTMs represent the bare ground of the terrain, a digital surface model describes the height of the vegetation, for example trees, and a man-made feature, for example buildings. It is thus important to distinguish between the DTM and DSM over vegetated or built area. A closely related term is digital elevation model (DEM), which is sometimes used synonymously with DTM, but often as an umbrella term to describe both DTM and DSM. DEM is often used for elevation models from remote sensing, example the radar or the photogrammetry. These models are rather DSM than DTM unless vegetation and building heights are removed. DTMs, conceptually introduced more than half a century ago, are today in a wide use in geodesy and beyond to approximate the Earth's relief for a broad range of application. DTMs are publicly available with near global coverage from satellite based mapping machines, notably the SRTM and the ASTER, at 1 to 3 arc-second resolution and 10 to 20 meters accuracy. In the near future, new commercial DTMs from the TAN-DEM-X and ELOS missions will provide more detailed terrain information than currently available. At national level, DTMs exist for many countries at varying resolution, mostly from ground-based, airborne LiDAR and photogrammetric surveys. On a planetary scale, a high-resolution DTM information is available for Moon, Mars, Venus and other bodies.